All right. Good morning, everyone. We're here with Aurora Caselli, and it's her last day with us here at AstrotwinColo, at the AstrotwinColo first week of courses. This is the first session of the day. We have two theoretical sessions and then the practical sessions after. So I'm going to leave you with Aurora. If you need anything, I'll be here behind the scenes, and I'll be paying attention to the chat on our YouTube channel, so I can pass along the questions that you may have to Aurora. All right? So, the floor is yours.
Okay, great. Thanks for the introduction. And I'm excited to be here for the last day. So let me share my screen. Okay. Great. So today we're going to be talking about another application of high-resolution spectroscopy. We started talking a little bit about characterizing exoplanets yesterday with high-resolution spectroscopy, and we talked about the Rossiter-McLaughlin effect and how you can measure the spin and the orbit coupling of the planet and the star. And today we're going to continue talking about exoplanets first, and we're going to talk about how you can measure their transmission spectra with high-resolution spectroscopy, also their emission spectra. And then we're going to move on and talk about measuring abundances of different elements and molecules with spectra and a bunch of different applications of that. So yesterday, before we start with going back to exoplanet characterization, yesterday we also talked about discovering exoplanets with the radial velocity technique. And I got a really nice question about what happens if there's multiple planets. So I thought I'd make a quick slide to talk about that. So this is data of a star, Upsilon and I think it has 2 planets, but it has multiple planets. So you can kind of see here, each of these points is a data point, and the black line is the best fit model that they find for all of their data points. And they find kind of 2 periods. You can kind of see this kind of shorter period that's going up and down, and then you can kind of see a longer period on the year or so time scale. And they didn't have a Loam-Scargill periodogram in this paper. So this doesn't correspond to the data that we're using here, but I just thought I would also show you what a Loam-Scargill periodogram looks like. So basically this is showing for all of the different periods, you basically fit a sinusoid. So you can fit this up and down. And then some periods have more power in representing and fitting the data. So that's what's shown here. So we can use a sine curve with a period of 10 to the 1, or we can use a sine curve with a period of 10 to the 2. So each of these points is a different sine curve that basically has been tested. And then the higher the power, the more likely that that sine curve fits the data correctly. And so again, this is a different planet, but you can see this is their detection of a planet with a period of 38 days. And so what you can often do is you fit your data and you find your best fit peak. And then you remove that sine curve. So you remove one of the variations. So maybe for this one, the strongest variation is this shorter signal. So you remove this shorter signal. And then you do another Loam-Scargill periodogram, and something like this, which maybe is not statistically significant when there's 2 signals, will become stronger and will become a detection after you remove the initial stronger peak. So this is kind of how we fit radial velocity curves with multiple planets. And then also when I was making this, I thought of one other cool application of radial velocities that I didn't talk about yesterday. So yesterday, I really only talked about radial velocities for eclipsing binaries and transits. So trying to use this wobble method to measure masses. But when I was working on my slides today, I also was looking at apogee data. So we'll use this later, you'll see. And they have this really cool plot, which is showing radial velocities for 100,000s of stars in the Milky Way. And they're plotted here. And by looking at the radial velocity, we can kind of start to see the kinematic structure of the galaxy. And so this is kind of how we can map stars into halo stars and bulge stars and disk stars is by looking at their velocity distributions. So again, we'll talk about apogee later because this is the data we're going to be using for today's lab. But apogee, instead of trying to get extremely precise radial velocities for a few stars and trying to measure those over time to find exoplanets, they are trying to take spectra of as many stars in the galaxy as they can. And so you don't need quite as precise radial velocities, but you still do need pretty high resolution. So it's a resolution of about 22,000 in order to get these radial velocity precision that we have here. Okay, so now moving on to what I wanted to talk about today, which is transmission spectroscopy first. So in general, transmission spectroscopy, what happens is the exoplanet passes in front of the star like a regular transit, and some of the light from the star goes through the exoplanet's atmosphere. And we can look at this at different wavelengths and see how the transit depth or the size of the planet changes at different wavelengths. So here's a video. It's just short, and it kind of shows you what that looks like. Okay, I'm going to play that again and talk while it's going. Okay, so the planet transits, and you can see on the bottom, they're showing the brightness. So in green, they're showing at 2.1 microns that the transit depth is small. And so that means that at 2.1 microns, the atmosphere is pretty thin. It's only this very small green circle. But at 1.8 microns, the atmosphere looks a little bit bigger because there's something in that region something in that wavelength region that's absorbing there that's opaque. So maybe, for example, water has a band at 1.8 microns. And so the light won't be able to pass through that. And so the atmosphere will look bigger where there's water because you'll get more of the light being absorbed at that wavelength. And here, this is exaggerated, of course, but at 2.3 microns, the atmosphere looks the biggest. And yesterday, 2 days ago, we saw that at 2.3 microns is the main band of carbon monoxide. So maybe there's lots of carbon monoxide, and so the atmosphere is optically thick at 2.3 microns everywhere where there's carbon monoxide. So the exoplanet looks even bigger. And what's something that you have to remember when you're doing transmission spectroscopy is you're only looking at a very specific part of the atmosphere. You're only looking at the part of the atmosphere right at the edge of the disk. So when we talked about phase curves, we had the day side of the exoplanet, which is the whole front of the planet, and the night side of the exoplanet. And here we're basically only probing something called the terminator, which is the region that is right at the edge between the day side and the night side. And these hot Jupiters that we're looking at often with transmission spectroscopy, they're so close to their star that they've become tidally locked. So tidally locked is kind of the same thing that the moon is around the Earth, where we only see one face. So the rotation period and the orbital period have the same length. So on these planets, sorry, my dog is chewing my computer cord. On these planets, the day side is always facing the star, and that day side is not going to change. It's always going to be the same region. Okay. So this is what it actually looks like when you do transmission spectroscopy at low resolution. So this is data, I think, from the Hubble Space Telescope. And this is showing a transmission spectrum of a hot Jupiter exoplanet. And so each of these points here is a different wavelength, and they're showing you the transit depth. So in this plot, the transit depth is this decrease in brightness here. Okay. And so where we have a larger transit depth, you're going to see that that corresponds to some element or molecule being in the atmosphere. So at 0.58 microns, we have a large transit depth, which means that the atmosphere is very opaque at that point, and this is because of sodium. And so they can fit all of these different wiggles in the transmission spectrum and decide what things are in the atmosphere at the planet. And so here you're seeing a detection of water or titanium oxide. Okay, so that's transmission spectroscopy at low resolution. And now, since we're talking about high resolution spectroscopy for this class, what happens when you look at transmission spectroscopy at high resolution? So this image actually shows emission spectroscopy, which we'll talk about later, but it explains both of these well. And again, here's our planet going around the star. And so you can see when the planet is in front of the star. So if this was in front of the star, you'd be getting the light that passes through the terminator, so the region between the day side and the night side. Okay, and so what you do is you take spectra in time. So you take many different spectra over time. So here on the x-axis, we have time or phase, and here on the y-axis, we have the wavelength. And so this is very exaggerated, so you really wouldn't see a signal this strong. But you can take advantage of the fact that the exoplanet is moving way faster than the star is moving. If you remember from our center of mass equation, the larger the object or the more massive the object, the less its velocity is going to be. And so the star is basically still, but the exoplanet is moving quickly. And so what you can do is you can use that fact and try to resolve the absorption lines of the exoplanet. And you know its velocity, you know where it should be going. And so you can try to see its velocity path in certain molecules. So this is the planet's velocity is shown with the white lines. And they've already pretended that they've removed the star spectrum. So also you can see that telluric is in black and it's straight. And so that's because the planet is moving much faster than Earth's atmosphere is basically stable, and the planet is moving extremely quickly around the star. So it makes it easier to distinguish planet lines from telluric lines and stellar lines. Okay, so to go into a bit more detail about exactly how you do this, these are some analysis steps of doing high-resolution transmission spectroscopy for the exoplanet around Kelt 20. So at the top, I'm showing you a single spectrum of the star. So you take a spectrum of the star, And you can see we have one really deep, broad absorption line here. And the next thing is you want to take spectra at a lot of different phases. So because this is transmission spectroscopy, you're taking spectra right before the exoplanet passes in front of the star, and then every maybe 10 or 20 minutes, a different exposure as the planet is passing in front of the star. And the star's light completely dominates this. And so this is showing at different phases this same spectrum. And so you can see these darker black lines. This is the absorption line shown here. And this is just over time. So this is the same spectrum over time. And the star's spectrum is just completely dominating it. But what we can do is we can easily just divide out the average in time. And so what that does is it removes any signals that are constant in time. And like we said before, the star is almost constant in time over this observation. And so by averaging and dividing, we're basically removing the star's spectrum. The exoplanet spectrum should not be removed because at every pixel, because the exoplanet is moving so fast, any spectrum from the exoplanet is going to be at a different pixel in time. And so by averaging over time, we're not removing anything that changes in time, and we're removing everything that's constant in time. The only problem with this is that we do get, even though the telluric absorption lines are not changing position in time, they are changing in strength with time. Because at the beginning of the observation, you are looking through a different air mass as you are at the end of the observation. These observations are going to take, to watch the exoplanet transit in front of the star, you have to take spectra over many hours. And that means that the star is going to start probably at somewhere close to the horizon, and then it's going to reach a peak and then start to fall again. And because of this, when we look through different amounts of the atmosphere, we get stronger and weaker absorption from the atmosphere. And so what you can see here is we get a much more uniform picture of the spectrum, but there are still some features. So for example, this feature in the red box, you can see that we go from a darker line to a lighter line. And this is a telluric line. This is a Earth's atmosphere water line that's basically changing in strength over the course of the observation. And so we do have to remove those. And so we remove these based on a bit more complicated principal component analysis, usually. And we don't have to go into the details. But basically, once we remove the telluric lines, we kind of see basically what looks like uniform noise. And this is to be expected because the exoplanet signal is going to be something like 1/10,000th the strength of the star's signal. And so it's going to be hidden in this noise. So in order to find this signal that's hidden in the noise, we want to combine the signals of hundreds or even thousands of lines together to see if we can find the signal of the exoplanet. And so we're going to use this cross-correlation technique that we saw yesterday and that we practiced using yesterday again. So for example, if we want to find iron in an exoplanet, we can cross-correlate an iron line list with all of this noise. And so what we do is we take this spectrum, and remember, each row here is a different spectrum in time. So we cross-correlate the iron list with the first row, and we look at we record the cross-correlation function. And then we do the second row, the third row, etc., until we cross-correlate it with every row, and we have a cross-correlation function at every point in time. Okay, and this is showing what you would get. So this is actually from research that I'm currently working on that hopefully I'll submit this paper soon. But this is looking at a detection of iron in WASP-76, which is the exoplanet host star that we've been looking at a lot. And so each row here, again, is a cross-correlation function. So if you remember from our cross-correlation functions yesterday, Anywhere where the cross-correlation function has a maximum, that's where you would expect the radial velocity, the line list, and the planet to match up perfectly. So here we have some amplitude, and so we're looking for a positive amplitude because this is a match in the exoplanet spectrum with the spectrum of the iron line list. And on the black dotted line, this is the expected path of the exoplanet in velocity space. So at the center of the transit, the exoplanet is supposed to have a radial velocity of 0. And so that's exactly what we see here, because it's moving completely perpendicular to our line of sight. We can't see any of its motion. And these two dotted lines here, those indicate the start and the end of the transit. So we shouldn't see anything correlated either before or after the transit. But during the transit starts down here. So the exoplanet is moving towards us, which is exactly what we would expect if we were looking at a transit. So it's moving towards us. Then it's moving only perpendicular to us right when it's in the center of the transit, and then it starts moving away from us. And so this is exactly what we would expect if we were going to detect iron in an exoplanet's atmosphere. And so we can do this method for lots of different elements and molecules. And that's exactly what we do when we look at exoplanets with high resolution transmission spectroscopy. We check to see, we do the cross correlation with tens of different elemental or molecular line lists. And then we can say WAS-76, it has iron, it has magnesium, it has vanadium, it has titanium oxide, but it doesn't have sodium, it doesn't have water. And using all of that data, we can kind of put together a picture of what the exoplanet looks like. Okay, and so this plot is showing emission spectroscopy, and I was kind of talking about absorption spectroscopy before, but emission spectroscopy is almost the same thing, except for now, instead of looking at the light from the star that's filtering through the exoplanet's atmosphere, we're actually directly detecting the exoplanet's atmosphere. So we're actually directly looking for the spectrum of the exoplanet. And here, instead of, so before, before, we were looking at the region right around phase 0, so right around here. And you can see that the lines go away because we're looking at the night side. But if this planet is transiting, we would start to see lines from the sun's, the star spectrum going through the atmosphere of the planet spectrum. If we're just looking at the emission, the lines will go away at the night side, because the planet is not bright at the night side. But before, basically, we were looking at a region just right around phase 0. You can see my phases go from minus 0.06 to 0.8. Whereas here, the phases go from, we were only looking right around phase of 0.0. Now, when we're looking at emission spectroscopy, we can look at the full phase, and the lines are going to be brightest right around a phase of about half. So right before it goes behind the star is when the full day side is in view. And so that's where the lines are going to be the brightest. And we can do the exact same technique where we take spectra at lots of different phases. Here we can have a much larger phase coverage, and we can take spectra at all of these phases. Do the same thing where we remove the star's light, since the star is not moving much. And again, do the same thing where we cross-correlate a line list, this time looking for emission from the planet. So it's a very similar process. Okay, and so far, high-resolution transmission and emission spectroscopy has been able to find tons of different elements. So in exoplanets so far, we found sodium, titanium, calcium, iron, vanadium, chromium, scandium, magnesium. I don't even know the names of some of these, but we found tons of different elements just by cross-correlating the different line lists. And we've also found lots of different molecules. We found water, we found carbon monoxide, we found titanium oxide, we found HCN, we found methane, and we've also seen evidence for hazes. So if we go back to our low resolution spectrum, they start to see this increase here at blue wavelengths, and they say that this is probably because of a haze. And a photochemical haze basically creates this slope in the blue. So we've also seen this similar photochemical haze at high resolution. Okay. And besides just looking for different elements and molecules, there's also some other cool things that you can do because we have such fine velocity resolution. We can start to look for atmospheric dynamics. So once we measure this iron feature, we can start to see if the iron feature that we measure has the exact velocity that we expect from just doing our initial calculation. If the atmosphere was completely still, we would see this velocity, radial velocity shift. But what we've done is, because we have this fine velocity resolution, we can actually say that the signal that we measure is slightly shifted from what we would expect. And what we've attributed this to is winds on the exoplanet's surface. And so we've measured wind velocities up to 10 kilometers per second on some of these exoplanets. And to put that into context, that's 100 times faster than any wind speed has ever been measured on Earth. And what we think is happening is because these exoplanets are tidally locked, they have a day side that's always being illuminated by the star and a night side that's never getting any of the star's light. What happens is you create this wind that's blowing from the exoplanet's day side all the way to the exoplanet's night side, trying to redistribute the heat. And we've measured this wind on a bunch of different planets so far. And another cool thing that we've done with high resolution spectra is we've been able to detect that some of these exoplanets that are really close in are actually evaporating. So because they're so close and the host star's energy is so intense, they start to develop a tail behind them of evaporating hydrogen and helium. And we've detected this evaporating helium on some of the exoplanets so far. And so we can see that these planets are just so hot that they're losing their atmosphere. Okay. Oh, I see that there is a question. So before I move on, I can answer that. So the question is transmission spectroscopy applied to specific types of stars, or is it reliable for any type to detect a planet's atmosphere? So yes, theoretically, you can do transmission spectroscopy on any type of star. Any planet that is transiting the star, some of the star's light is going to go through the planet's atmosphere, and theoretically, you would be able to detect that signal. Now, it depends on, like I said, you're already looking at a very small signal. It kind of just looks like noise here. And so in order to maximize that signal, we really have only been able to do this on the biggest exoplanets so far. So we've been able to do this on hot Jupiters and down to Neptune-sized planets so far. We still haven't been able to do this on any Earth size or even super Earth size planets so far. And about the stellar spectral type, ideally, this is also best to do on stars that are quiet, so stars that aren't super variable, because any sort of signal you have from the star's variability is going to make detecting these lines a lot more difficult, because already we need thousands of lines and we don't want any sort of radial velocity jitter from the star, because that wouldn't be, if the star, if there's radial velocity jitter in the star and it's changing in time, then we wouldn't easily be able to subtract off the star's spectrum and be left with the exoplanet spectrum. You'd be left with a lot of noise. So in practice, for example, looking at WASP-33. WASP-33 is an exoplanet that's going around a delta Scuti star. And we have been able to, that's one of those pulsating A-type stars. We have been able to characterize its atmosphere, but it is a bit more difficult because of the pulsations. You really have to be careful when you're doing the transmission spectroscopy. So yeah, ideally you want a large planet around a smaller star that's going to give you the largest signal, and you want the star to be relatively stable in radial velocity. Okay, hopefully that answers that question, but let me know if you have more. I don't see any other questions about transmission spectroscopy yet, so I will move on. Okay. So for the rest of the lecture, I'm going to be talking about abundances. So at high resolution, we can look at the individual line shapes. And like we talked about on Wednesday's class, the line depth or strength is set by a few things. So one, the temperature, and that tells you how much of the element is in the correct energy level or ionization state to make that specific absorption line that you want to look at. So if you remember our example that we talked about a bunch, if you want to look at the hydrogen alpha line, which is an n=2 energy level to n=3 energy level, you want to look at stars that have temperatures of about 8,000 Kelvin, because that's kind of the sweet spot before a lot of the hydrogen has become ionized, but when a lot of the hydrogen is in the n=2 state, which you need. Okay, so you need the correct temperature in order to get that element or molecule to form. And then we also have to think about how some transitions are easier than others. So yeah, there's forbidden lines that are going to be difficult to excite, and that type of thing. So if we're comparing different lines, if we're comparing one magnesium line to one iron line, we have to keep in mind that maybe the line depths will not always be the same, because one of the lines is easier, the transition is easier to do than the other line. And then the last thing that sets the line strength is the abundance of that element. So if you have more of a certain element, you're going to have a deeper line. But if we compare stars that have similar spectral types and temperatures, and we compare the same line between multiple stars, we don't have to care as much about the first point and the third point. And the line strength is mostly going to be set by the abundance of the element. Oops. Okay. And to do this, often we don't need the very highest resolution spectra that we've been talking about before. So these really high precise radial velocities, they need extremely high spectral resolution. All we need for this is enough spectral resolution to be able to distinguish individual lines from each other. We don't want the lines to be overlapping, but we don't need that extreme precision radial velocity. So spectra that are best for abundance measurements are somewhere between a few thousand to a few tens of thousand. And again, this is the spectra we're going to be working with today are from the Apogee survey, and that's a resolution of about 22,000. And so that's kind of a really nice resolution where you don't have to waste as much time with the extremely high resolution, because the higher the resolution, the more time you need to expose on an object. But you have enough resolution that you can distinguish the individual lines. So in order to measure the line's strength, we need some metric to measure how deep the absorption line is. And so usually what is used is the equivalent width. I'm sure that you learned about equivalent width in your introduction to astronomy class. But basically, if you have a spectral line that has kind of a Gaussian or Lorentzian shape, you have some amount of absorption happening, and then you have in the center, and then you also have these wings. And the equivalent width basically just takes the area in the absorption line and says, if it was the full intensity, what would be the width of this box that would give you the same area that's in this spectral line. And what's a cool thing about the equivalent width is it's not affected by broadening. So a broadening mechanism, like for rotational broadening, for example, it takes some of the photons that are absorbing at the central wavelengths and just, sorry, not the photons. Yes, the photons. It takes some of the photons that normally would be absorbed at the central wavelength, and they're just absorbed on the wings. But there's still the same amount of total absorption happening. It's just redistributed. And so the equivalent width, basically, it doesn't matter if the photons are being absorbed on the wings or in the center. As long as the line is not saturated, it's not affected by broadening. Okay, so that's what happens if the line is not saturated. And by saturated, I mean the line goes all the way down to intensity of 0. So this red line here is not saturated. But as the line starts to saturate, this isn't the case. So the abundance is proportional to the equivalent width when the line is not saturated. That's what this means. Abundance proportional to equivalent width. But once the line starts to saturate, now we have a slightly different relation. So now the square root of the natural log of the abundance scales with the equivalent width. And then once we get to be very saturated, the wings start to deepen, and then you're in a different regime where the abundance is now proportional, sorry, the square root of the abundance is now proportional to the equivalent width. So you have a few different regimes for lines. The easiest thing to do is to just measure absorption lines from lines that are not saturated. So the best lines to measure these these abundances are narrow lines that are not too deep. So you don't want something that's too deep. You don't want to use kind of the main transition because that has the negative effect that it could become saturated and you get these more complicated relations. But in general, the equivalent width is proportional to the, for non-saturated regimes, it's proportional to the abundance. So if you measure an equivalent width that's double from one star to another star, then you can probably say that the abundance from that star to the other star is doubled. Okay, and some cool applications of measuring abundances has to do with the chemical evolution over time. So this is the periodic table, except for all of the different elements are colored by how they're created. So in the Big Bang only created hydrogen, helium, and a little bit of lithium. Every other element was created after the Big Bang as stars enrich the gas and the dust. So you can see here that exploding massive stars have created a lot of the elements up to maybe 35 or something. And dying low mass stars and merging neutron stars have created a lot of the even heavier ones. And what's important to note here is timescales. So the first thing that's going to happen is Big Bang, obviously. But then in order, so high mass stars have much shorter lifetimes than low mass stars. And so high mass stars are going to be the first thing that's going to enrich the gas and the dust of the universe. And so everything colored in green is going to be one of the first things to enrich the gas and the dust. In order for low mass stars to die, or for white dwarfs to explode, because white dwarfs are made of low mass stars, you need a lot more time to go on. And so these two things kind of happen second. And so we get kind of all the elements in green happening first, and then everything that's in yellow and blue, that kind of gets enriched later. And what that's created is a solar abundance that we see in the present day. So this has every element and its solar abundance by atomic number. So you can see hydrogen and helium are obviously the most abundant, and this is log abundance. And then you can see that as we get to higher and higher atomic numbers, things become less abundant. And an interesting thing is that actually iron, you get this peak here at iron. So iron is actually more abundant than even magnesium and aluminum, even though those have lower numbers. Oh, I see that I have another question. Back to planets. So let me finish explaining this, and then we'll go back. And so oftentimes people will talk about metallicity, or the iron to hydrogen ratio. And whenever people talk about this, they're talking about the scaled solar metallicity ratio. And so oftentimes you'll see Fe over H is equal to -2. And this means that there's 10 to the -2, or 1/100th times the present solar iron to hydrogen ratio. So they're not telling you that the iron to hydrogen ratio in this star is 1 to 100. They're telling you that the iron to hydrogen ratio is 1/100th of the solar iron to hydrogen ratio. So it's a bit confusing, but you just have to remember that everything's being compared to the solar ratio. Okay, so let's go back to the tidal locking so I can answer that question. Okay, here is our planet, and we have the star and we have the hot Jupiter. And so tidal locking basically is something that's always going to happen over time. It just depends on how long this is going to be. And so hot Jupiters, because they're so close to their star, the time scale for tidal locking is really short. And so almost every hot Jupiter that you're going to see is tidally locked. And you can calculate the time scale for tidal locking for each of these planets. But as a rule of thumb, any hot Jupiter that you see is going to be tidally locked. Even I think all of the sorry, I'm blanking. No. The TRAPPIST, there it is. Even the TRAPPIST, low mass star with those super Earth planets, I think most of those are expected to be tidally locked based on the tidal locking time scale. And I can talk about this more later if this doesn't fully answer your question, but I'm just going to move on for now. Okay, so remember, metallicities are always in comparison to the solar abundance. And I kind of just briefly explained to you why the abundances have changed over time, but we can actually measure this. So here's a plot that's showing the iron to hydrogen ratio. And again, this is the same 10 to the -2 means 10 to the FeH of -2 means 10 to the -2 times the solar iron to hydrogen ratio. And you can see that basically ages that are really old, so around 12 gigayears at the very beginning of the universe, on average, the iron to hydrogen ratio was about -2. And then pretty quickly, by about half the age of the universe, so 6 billion years, 6 gigayears, we have metallicities that are maybe about -0.5. And in present day, even for the last billion or 2 billion years, almost everything that we see is metallicities of about the solar metallicity. And on average, because the dust and the gas is being enriched by the same processes, supernova and massive stars, on average, the abundances of most elements scale linearly over time. So here's a plot showing the equivalent width of calcium. It just says W, but this is showing the equivalent width of calcium versus the iron to hydrogen ratio. And you can see that as calcium becomes more enriched, so does iron and hydrogen. So does the iron to hydrogen ratio. And so because of that, we often just say, what is the total metallicity? And we can use this Fe over H ratio to describe how everything scales. So we just scale every single element that's heavier than hydrogen and helium with the same ratio. But if you remember how I showed you that we have kind of these two different processes where we have exploding massive stars and white dwarfs and low mass stars, which happen at different times, there is a slight relationship between some different elements that scale slightly differently. So some of the elements that are much more common to be made in massive star explosions, for example, sodium, magnesium, oxygen, titanium, they're made preferentially early on. And so compared to the solar value, magnesium or titanium is enhanced compared to the iron value early on. So here, that's what this plot is showing. Here, now we're showing the titanium to iron abundance scaled to solar. So up here, we have higher titanium abundances to iron abundances than we do in the current solar abundance. And we're showing here with the circles, or the plot is showing here with the circles, the age. So we have most of these kind of larger circles, which means 15 billion years, at higher titanium abundances. And then as we get to the current day, you can see that the titanium to iron abundance is about the same as the sun's. So at lower metallicities or larger ages, titanium and magnesium and these other elements are going to be more abundant than they are in the sun, or not more abundant than they are in the sun, comparatively more abundant than they are in the sun compared to iron. Okay, so elements that are created from exploding white dwarfs or low mass stars, you have to wait until these low mass stars die, and that takes a lot longer. And elements that are preferentially made in exploding low mass stars, sorry, not exploding, in exploding white dwarfs or dying low mass stars are iron and cobalt, rubidium, and more. And so by measuring the elemental abundances over time, we can estimate stellar ages. And this is really cool because measuring stellar ages can tell us about the galactic formation and the galactic evolution. So here's a plot from the Sloan Digital Sky Survey. And this is showing the different ages and metallicities of stars in the Milky Way. So at the bottom, you can see that in red, we have the disk. So this is the thick disk at the bottom. And most of the stars that we measure in the thick disk are red shape, are red colored, which means that they're young and they have a metallicity of about -5. As we get to higher and higher elevations above the disk, we start to measure lower and lower metallicities until we get up into the halo of the Milky Way. And the halo, we see on average metallicities of about -1.5. So these stars are very old. And so we can then put this information together and create a picture of what happens in how stars age in the Milky Way. And so now we know that the general theory is that stars are born near the disk in the center of the galaxy. And then slowly over time, they're heated, which means that they have random gravitational interactions and their orbits become higher and higher. And this is what kind of creates the halo population, where you have these older, gravitationally heated, doesn't have anything to do with actual heat or how hot they are, but you just call it dynamically heated often. And so that means that their orbits are much higher and they're part of this halo population. Okay. And another cool thing about low metallicity stars is that they have different properties. They can have different properties to regular solar stars. So this is a study that I did back in graduate school where I looked at M dwarfs and looked at how their properties change based on their metallicity. So just to show you what some low metallicity stars look like, over here, all of these stars have spectral type M3. But you can see that the spectra look really different. So here we have decreasing metallicity. So this is solar metallicity all the way down to metallicity of -2. And an interesting feature is that as we get to lower metallicities, the titanium oxide line disappears, whereas the calcium hydride line stays pretty similar, or the calcium hydride molecular bandhead stays pretty similar. It slightly decreases, but it's pretty similar, whereas titanium oxide basically completely disappears. And so this is how oftentimes we can quickly estimate a star's overall metallicity is by looking at these large features. So then what I found is that for a given effective temperature, so each of these points here is a star in the sample that I looked at, and they're colored by their overall metallicity. And for a given effective temperature, the radius of a star can change by up to a factor of 5 for different metallicities. So for the lowest metallicity stars to the highest metallicity stars. So for example, this star down here has a metallicity of -1.75, and it has a radius of about 0.1 times this radius of the sun and an effective temperature of 3,600. Whereas a solar metallicity star has the same effective temperature, a metallicity of about that of the sun, but a radius of 0.6 times the radius of the sun. So that's a really big difference. So if we're trying to have different radius to temperature or spectral type to radius relations, it is really important to take metallicity into account as well for very low metallicity sources. You can see that if you're just looking in the solar neighborhood, so like right around 0, everything kind of follows the same relation. It's not until you really look, and almost everything in the solar neighborhood, so everything close to the sun, has metallicities very close to 0. It's not until you look at these halo populations that you really need to start taking this into account. But when you do, it's really important that you do take this into account. Okay. So now that we've talked about metallicity in stars, there are some cool applications that we can talk about how metallicity affects different things. And so we can look at the metallicity of stars that host exoplanets and see how properties of the planet systems that form depend on these stars. Okay. So this plot up here we'll start with, and this is showing all stars. So each dot here is a star, and the blue dots are the stars that are have metallicity less than minus 0.1. So remember, we're still like way up here, and all of the stars that we're looking at are basically solar. So all of these stars, we can see they have planets that have radii of between 0.5 and 4 Earth radii for the most part. As we start to look at stars that host planets, now we're looking between minus 0.1 and plus 0.02, so another bin. And we start to see now all of the planets in this bin are now colored blue. And so we start to see that we have a few hot Jupiters. As we increase to metallicity, again, it looks like kind of the whole distribution is shifting up. And again, the whole distribution shifts up. And finally, for the highest metallicity bin, metallicity is greater than 0.13, we start to see a ton of these hot Jupiter planets. And so this paper concluded that metal-rich stars are more likely to host hot Jupiters than metal-poor stars. It's still really unclear if there's any trend with metallicity for Earth-like planets. It seems like both low metallicity and high metallicity stars can make Earth-like planets. So this trend kind of needs to be explored further for Earth-like planets. Okay. I think I will stop here since we have about 4 more minutes, and I'm going to move on to the next topic after the break. So if you have any other questions, let me know.
All right, so we'll continue in 15 minutes at 9:15.
Okay.
Right?
Yep.
Okay.